For topic 9, we're going to be looking at more on quadratic equations. Recall that a quadratic equation takes the form of ax squared plus bx plus c. Now, I know that has a lot of letters in there, and math is generally better with numbers, so an example might just be 3x squared plus 7x minus 2. Any of these numbers can be positive or negative in the A, B, or C spot. It also could be that a quadratic might look like x squared plus 7, or just maybe 4x squared minus 2x. All of those are quadratics. These last two just happen to have b values that are 0 or c values that are 0. So a piece can be missing, but if it's a second degree equation, then we know it's a quadratic. Another key vocabulary word that we want to look at is a zero of a function. That is where the graph of the quadratic crosses the x-axis. So let's say if I were to make a grid here and have a graph of a quadratic, wherever it is hitting or crossing the x-axis, we call those zeros or x-intercepts. These are also the places that if I had an equation for this graph, let's say this graph is called f of x, whatever the equation is, whenever that function equals 0, that is how we find our x-intercepts. So let's look at a couple ways that we can find where a quadratic hits the x-axis by solving when the function equals 0. One of the easiest ways to visually see a solution to one of these quadratics is to look at the graph of it. So we're given the equation or the function x squared minus 16, and we want to know when that quadratic equals 0. That is where it crosses the x-axis if we were looking at the graph. So if we come over here and we see the graph is plotted here on Desmos, our x squared minus 16 crosses the graph here at -4 and at +4. So by using a graph, our tasks becomes quite simple. Just find where the graph hits the x-axis, and we would say when x equals 4 or x equals -4. And that makes sense in our equation, because if you think about taking a 4 times 4, you'd get 16, and subtracting 16 would make 0. Same thing with a -4. A -4 squared minus 16 would make negative times negative be a positive 16. So we can check that just when we plug in a 4 or a -4, it does in fact make our equation become 0, but we were able to easily see that on our graph as it crossed the x-axis. You can try these other examples in your packet, but remember, the biggest idea is you can always go back and use Desmos to graph them, and you would figure out where they would cross the x-axis if it asks you to find the solutions for when this quadratic equals 0. Now, when we want to find when a quadratic equals 0, again, it is always an option to graph it. So you'll see here I have graphed on Desmos my quadratic, and I note that it crosses at 1 and 6. So I know my solutions here would be at x equals 1 and x equals 6. But it didn't ask us to use the graph, although we can sure check. It asked us to use a table this time, and if we were using a table, we can make Desmos create that for us. When you're in Desmos, if you type your equation first and then click on this little settings, we can pick the table option and it will convert it to a table for us. Now let's think about what we're looking for. We're looking for the solutions. That is, what x values can we plug into this quadratic and have the output be 0? Remember, x is our input, therefore y is our output. And so we want to look here, whenever the y value is 0, that would be our solution for the x value. So we can see 1 is an option. Now right here, I do have x equals 1 as one of my solutions, and I got that from the graph. Luckily with Desmos, it gives you a picture of the graph as well. But if we weren't sure where the other one was, we're going to type in further numbers here and see if we can find another place where it has a y value of 0. And sure enough, that happens when x equals 6. So using a table and solving one of these quadratics, you'd be looking for when the y value is 0. And we see that happens when x is 1, so there's our first solution, and when x is 6. It should be noted that I did use the graph to give me a little hint to look for it, but make sure you're able to look at a table and tell where the solutions are located. Now, while equations are nice and using a table seems pretty reasonably easy, I did graph or make a table of part B here, 3x squared plus 5x minus 2. And I've converted it to a table. We can see right off the bat here that negative 2 is an input for x that would produce an output of y equals 0. So I could say that one of my solutions is x equals negative 2. The tricky part about tables is, notice how all of our inputs for x are whole numbers, like 1, 2, 3, 4. There's no decimals. If I look at the graph, because luckily Desmos provides that along with my table, I can see my second x-intercept or solution is going to be a decimal. This would be a lot trickier to find if you didn't have the picture. So I happen to know that 0.33 repeating is 1/3. But had I not known that I'm looking for a decimal, this would have been a lot trickier to find. I would have had to have known that I'm going to type in a 1/3 for my x value to get a y of 0. So tables can be helpful, but many parabolas don't cross at the x-axis at whole numbers. So it's important that we have other methods to help us find these solutions to the quadratics. A quick application problem here for us has a gal hitting her golf ball off the tee, and the height is modeled by the quadratic they give. So if we were to look at a golf ball trajectory, generally the ball will go up in the air and then eventually landing on the ground. This little note here in the picture is helpful to remember that when it hits the ground, the time it will take will give me a height back at 0. So the ball starts at 0, 0, we could say, or wherever it does, maybe 1 inch above the ground. And I can tell it's going to start 1 inch or whatever unit they're using above the ground because of this C value. So when we graph it, it's going to start a tiny bit off the ground on the tee, fly into the air and peak at the top and then come back down. They're asking for what time that will be. So for us, that's what x-axis value, or 0, will the quadratic have when it hits the ground. So we're going to go ahead and graph this real quick. And while they may ask you to use the table, let's stick with the graph for now, because when we notice here that the ball starts at a height of 1 on the y-axis and peaks up to the top and comes back down, it takes approximately 5.04 seconds. So that will be our other solution, and that would be pretty tricky to find if you were using a table, because we wouldn't know how far out we want to go on the decimals. So we'll use the graphs to help us solve it. Lastly, let's note how many solutions a quadratic can have. Any parabola could cross the graph twice, like we have seen, where say it goes, we could do a negative parabola, it hits the graph twice. That would be 2 solutions. A parabola also could be happy or sad and touch the x-axis just 1 time. And so that would have just 1 solution or 1 x-intercept. But consider a graph that would never touch the x-axis. It might look something like this. There are parabolas or quadratics that have no solutions, and we'll spend the rest of this topic looking for ways that we can find those x-intercepts besides just the graph or the table.